Introduce yourself and tell us what you're going to talk about.
Yeah, I'm Rick Carback. I work with quantum computers now. In Zcash land, I'm best known as a Mixnet guy. Um, my fondest memory, fondest and sort of most regrettable memory with Zcash is I came to a conference much like this, and about an hour before I was supposed to talk, they had announced, I forget who it was, but one of the Tornado Cash or Samurai Wallet guys got arrested. And I was going to announce how you can use, like how I was planning to launch my Mixnet for like 5 cents a transaction. You could put shielded Zcash transactions through the Mixnet. And I was told in sort of no uncertain terms by an unlisted number, if you make money on crypto right now, the government will come after you. You are a U.S. citizen and we will pay. And I was like, shit, okay, not going to announce that. So that's my fun Zcash story for you. I know one of the previous speakers said, sometimes it feels like the deck is stacked against you, and in especially the private space, that is true. There is government activity, and they're trying to suppress it sometimes. Sometimes they're not. I don't know. I think these days, if you're sort of a large project and you're doing a lot of different things, we're gonna hear from NIM after I speak, I believe, and they're doing exactly what I was proposing all those years ago. But these days, and academically, I'm sorry, I didn't finish my intro. I did a lot of civic tech. So my PhD thesis is in privacy enhancing electronic voting systems. So you get a receipt when you vote, but it doesn't prove how you voted, which obviously is a Mixnet based platform. So that's a little bit about me. These days, I work in quantum computers. We are largely building a platform to sell quantum compute. We're building the world's shared quantum computer because you can take qubits, and you've heard of this term called entanglement. You can entangle qubits across the distance. And what that means is we take different quantum computer installations and entangle the qubits across fiber optic cable. So our ultimate goal, our vision, is to get that. So for those of you who are Zcash people and you're worried about privacy, the too long didn't pay attention to this presentation is switch to Orchard and hope that U7 comes quicker than it's been coming, and be ready to upgrade anytime there's an upgrade so that you are on U7 as fast as possible, and hope that they actually fix things in like U8 or U9 of the protocol, because Zcash has problems, and I'll be telling you more about that. So the problem here is quantum computers can break ECC crypto. ECC crypto is what essentially all modern privacy technology is built on, with a few exceptions. So hash-based ZK starts are one of the exceptions. There's very few of them. The trade-off tends to be when you're using these hash-based methods, key sizes are massive, the resources required are significant. So that's sort of the problem we're dealing with here. The other problem is everyone thinks that it's like 5, 10. Well, the current thinking is 5 years away. The thinking up until about 2024 was that it was always 20 years away. And the last 3 years, it went from 10 years to 5 years. And my personal opinion, that's my website, thequantumdoomclock.com, is if you look at the exponential growth, and you look at the error correction rate improvements over the last couple of years, you're seeing two things exponentially growing in opposite directions. And you're going to enter this gray space in 2028, specifically March 2028, according to like the raw data I have, where it's not going to be clear that a quantum computer is in that state where it can break crypto or not. And then after that point, you're just going to have to like throw your hands up in the air and say, maybe what I'm doing is broken, but maybe it's fine. And hopefully a few years later, we'll find out one way or the other. A great example of this kind of thing that happened most recently, about 2 months ago, Google released a paper. They said, we've pushed the required number of logical qubits. So there's this concept of a logical versus a physical qubit. You used to need like several 100,000 physical qubits. That was 2024's number. 2026's number is 30. So that's a big improvement. And that's from Alice and Bob. They say they're going to release a computer by the end of the year that they're going to be able to implement a logical qubit in 30 physical qubits. So the logical qubit count required went from about 1,800 to break ECC
all the way down to about 1,400 in their number, 13 to 1,400 in their numbers. And now it's 40% lower 2 months later and they published all this under a zero knowledge proof, but people figured out how to like essentially get around that because there's enough public information that it just derived the right process. So we're already 44% better than Google's numbers 2 months ago. So this is kind of like the exponential problem. And then the person who has been the most vocal and the person all the news articles cite saying, oh, quantum computers are always 20 years away from crypto. He just published that three months ago saying, don't say I didn't warn you. Like, I don't know what's going to happen in the next couple of years. So with that, this is just illustrating the point. Like, yeah, it looks really flat until you see you get a little bit more progressive and everything builds on it. We're finance people here mostly. I hope we would understand like compound interest. But like this is like compound interest on steroids. It's literally a doubling or tripling in the span of a year. And we don't have very far to go. These are numbers from 2025 when it was like about 1 million physical qubits that you needed. And now it's like a little closer to like 600,000. So those lines are going lower and the number of qubits is going up. Since this is a technical audience, I actually get to teach you like why and how quantum computers work. So what this slide is showing you is essentially like an adder array gate on a quantum computer. And we are doing this thing where we are looking at these 3-bit inputs and we're determining whether they're constant or balanced using those definitions on the screen. I'll let you read that. And when you run the quantum computer, you run this Hadamard transform gate on all the things. You run the function. You run the Hadamard transfer gate again, and you do this like little twist on them, and then you read it, and you get the answer. So how many times does that algorithm run? So the circuit lights up, runs through it once. Now, when we make the problem bigger, like let's say we're going to do 4 bits as opposed to 3 bits. Yeah, I need another qubit, right? But it's a constant time algorithm, whereas this is going to explode exponentially. Right, so it's a massive amount of additional work that you would have to do on a classical computer. And what you're doing, like the mental model you should have with quantum is like a 2D grid and like a line, right? And a classical computer has to go a little bit in the X direction, a little bit in the Y direction to get to the end state value. And the quantum computer just goes right there in one step. And that's not true, like generally speaking, for all algorithms, but there do exist this class of algorithms, of which the discrete log problem is one of them that causes this problem. The great thing about it is that this is all going to change the world, right? So there's applications in finance, there's applications in logistics. If you were here 2 days ago at the hackathon, we showed you finance optimization where we figured out what crypto was optimal to use to buy your bit refill cards. We used the actual quantum computer that we have access to do that. So it can run these problems right now. I mean, obviously, you can run either a simulation or the exact same computation classically right now, and it's about the same. But once you get past about 50 qubits, it becomes impossible to do the simulation. And then on the classical side, to keep up, you have to start doing, estimations of the algorithm for it to work. In privacy, we have a bigger problem, which is harvest now, decrypt later. 10 years ago, I said, oh, well, we'll do some things where we'll do some hash-based signatures, and then the signatures will be secure. And for key agreement, we'll add some things in there to sort of prevent it from being breakable after the fact. And I proposed some things, wrote some things, published some code, and said, well, it's probably 30, 40 years away still. I'll be dead, most likely, or I'll be retired. It's not going to matter to me. And in fact, in grad school, I literally had a professor say, we're going to talk about quantum computers today and why they're relevant to crypto. It's like one lecture. He said, don't worry about it. It's probably not you. It's going to be your students or their students that are going to be worried about this. So never really thought I would be here in this moment. So the hardest now to decrypt later problem is we can take encrypted data today, like the Zcash transaction, the shielded Zcash transaction that we did earlier at the beginning of the talks. And we can look at that encrypted data and we can uncover what what's happening there after the fact. Which all crypto kind of has that vulnerability, but typically we say, oh, it's going to be 30, 50, 100 years. That's like a cryptographer gets uncomfortable when you say it's going to be computable in 30 years. They're generally comfortable once you say it's decryptable in like 50 to 100 years, right? So like that tends to be what most crypto is rated for, is like 30 to 100 years. But we're going to be in this period probably in the next 5 to 10 years where everything the previous 5 to 10 years is going to be decryptable. And that's a big problem for privacy crypto because basically all of it, with a couple of exceptions, is vulnerable in one way or another. Proof systems, that's CK proofs. The stars are not vulnerable because they're hash-based. Message anonymizers, anonymous authentication systems, confidential ledgers, that would be Zcash, Monero. We're going to talk, Zcash is special, so we're going to talk a little bit about that in the next couple of slides. Multi-party computation, threshold encryption is vulnerable, and then encrypted aggregators, so like group signature type things, they're generally vulnerable. And there are essentially not a lot of solutions available right now. There are solutions available for the signatures, and there are solutions available for key agreement right now. That's what NIST has approved, but they rely on algebraic constructions that just haven't been figured out or just aren't workable in the current ecosystem yet. And so let's think about Zcash specifically. So these 3 boxes, transparent transactions, if you use it, your funds are stolen in the context of a quantum computer. If you're using Sprout or Sapling, in some cases your funds are taken. In some cases, we're able to counterfeit funds in the shielded pool. There is a protection in Zcash where you can't take out more funds than went into the shielded pool, but that's just like you're the bag holder. Like that's not a real protection. So be aware of that. On Orchard, the proof system is broken, but the privacy, if you never publish the spending key, which when you put the QR code spending the money, you publish the spending key, is protected if you never publish. So now your public keys are essentially, you have to treat them like secrets. So if you treat your public keys like secrets and you're using Orchard, you're generally speaking going to be okay on the privacy side, but the proof system is going to fail when a quantum computer comes over. And U7 fixes that. There's 2 main things. Tachyon is the one that fixes the privacy. They just remove the note effectively. I mean, I'm oversimplifying it, but they remove the note that would make it possible to do the decrypt, to break the key that would enable you to de-anonymize the transaction. And then on the left side, there's the ZIP 2005, which will recover the funds and protect your funds. But there's still this proof soundness problem that is up in the air. And hopefully, I think that there's time to fix it. I think, we do, even on my most aggressive timeline, March 2028, that's still about 2 years away. I do think we're going to be, generally speaking, okay. So this is the takeaway of the talk. Orchard preserves privacy, but quantum computer can still break that proof system. And that's what we need to be worried about. What do we do about it? I'll just say that privacy techniques go back a long way prior to crypto. There's a famous principle from a guy named Kirchhoff in 1883 and Claude Shannon. Do you guys know Shannon entropy or the imitation game, or the movie, just the guy that sort of invented a lot of the base principles of cryptography and a lot of mathematics as well. He coined the phrase, the enemy knows the system. So you have to operate as if the enemy knows the system. And we know that very well. And this is sort of the general advice. I already told you the first one, public keys are secrets now, so treat them as such. Compartmentalization, we had a great example of that where you have to share your viewing key on one of the tools. And so the general advice is use this for your public storefront, use a separate wallet for everything else. I think that's really good advice. Pseudonym, so build a wallet, use it for a transaction, throw it away, don't keep things around too long. Again, upgrade, especially when new crypto comes out. I know that there's there's kind of a double-edged sword in that the new crypto is generally not is less trustworthy. This is one of those cases where I would just upgrade immediately because, especially after 2028, I just don't know what's going to happen with the quantum computers. And minimizing expire is just kind of a summary of everything I just talked about. There are cryptographers, they are working on solutions. In general, the resources required are significantly more. And the confidential ledgers is the biggest one that I'm worried about. But I think that it is possible to solve these problems. I just don't know how it's going to play out. So I'm not worried on the long tail of crypto. In general, I'm an optimist, but I will tell you in 2024, when I realized like the trend that we were seeing, I went through a very deep, dark period of about 3 months where I just disappeared. And I was like, man, everything I've been working on my whole career, it's like bullshit now. And it took a while to get over that. And I realized, well, these things are really cool and do a lot of neat stuff. And they're going to have commercial applicability probably in the next year or so. I think that's really cool. With that, questions? I'm on Signal. You can find me. And I think I brought my business cards. I'll hand those out too if anyone's interested.
Thank you so much, Rich.